Right, so I'm going to go through the mock exam revision 1.1 in this video. I know I've got a video for 1.1, but I've done a smaller, shorter version for you lot to revise from, hoping that you'll actually watch it. So I'm going to go through these things here. So primary storage. What is primary storage? Well, it's very fast storage that can be directly accessed by the CPU. Okay, it's not what a lot of people say, which is non-volatile. A lot of people say, sorry, volatile. So volatile, non-volatile, if you remember, volatile means that the data's lost if you turn the power off, and non-volatile means the data's not lost if you turn the power off. And people often say that's the difference between primary and secondary storage. It's not, because one of the primary storages is ROM, and ROM is non-volatile. It doesn't lose the data when you turn the computer off, but a ROM chip is read-only. Okay, so you can only read from that. So obviously, if you can only read from it, it'd be awful if it lost its data because you can't write to it. So there are two types of primary storage, RAM and ROM. Okay, ROM generally holds the boot code for the computer, so it's enough code to get the computer loading up the operating system, right? There are other uses for ROM, storing settings and other things like that. But generally, the main use for ROM is to hold the boot up code. So when you turn your phone on, because computers have to execute code, right? That's what they do. They execute, fetch, decode, execute. That's what they do. So when you turn your phone on, it's got to fetch, decode, execute something. And so it runs something from possibly called the BIOS or the UEFI. There's loads of different ones. But basically, the boot code for the computer gets executed. And that's stored on ROM, on a chip. Right? And that can be accessed by the CPU. And the other one, obviously, for primary storage is RAM. So the thing about primary storage is it's very fast and the CPU can directly access it. In modern systems, the CPU cannot talk to secondary storage directly. It has to only talk to memory or ROM. If you want something from the secondary storage to be accessed by the CPU, you must first load it into main memory. Okay, so that's the difference between primary and secondary. Primary is very fast, generally smaller, and the CPU can talk to it. Secondary storage, obviously, it's the opposite of those things. Right, so the fetch, decode, execute cycle. Okay, the good old fetch, decode, execute. So as I said before, right, you've loaded the program into RAM because you can't access the secondary storage directly. So you've loaded the program into RAM. So you've got your program in main memory in here. Let's put these addresses out. Okay, and this is your game you're doing. This is some, add. These are sort of made up instructions, sub, load, whatever. Okay, random instructions, right? Now we need to fetch, decode, and execute these. They're in main memory. Okay, they're in RAM, but I'll say main memory as that's the proper term. I'll put RAM in brackets because they could invent a different thing, not RAM. Anyway, so how do we fetch it? Well, first of all, we need to know where we currently are, where was the last instruction. So the program counter is a register, which is a small bit of very fast memory, which stores the address of the next instruction. So if we were at 2, that would mean that we are here. Okay, so we've previously fetched, decode, and executed add. And we need to fetch, decode, and execute that. Well, how do you do it? Well, you have these two things called the MAR and the MDR, and they work in unison. And what you have to do, they are the things that can sort of talk to RAM. You put the address of what you want from RAM there, and then the data will end up there. So we would then, the first step of the fetch, decode, execute is to copy this into here. 2. Right, then you go fetch. Then that instruction will end up in the MDR. Right? So this MAR and MDR are the bits that can talk to RAM. Think of them as 2 boxes. One box you put the address of where you want to get stuff from RAM, and in the other box will appear the stuff you got from RAM. Right? And then of course you decode, execute, and then before you repeat the cycle, you would increase that by 1 so that it would move on to the next instruction. I have done a more detailed version of this on my other video, but I'll be honest with you, the exam questions don't tend to be very hard on this topic, which we'll see later when I go through all the exam questions. So there's the actual steps. The program counter address is copied to the MAR, data from main memory is fetched into MDR, the instruction is decoded, executed, and the program counter increments and the cycle repeats. If you get all confused by this bit, just put fetches from RAM, decodes, executes, program counter increments, and the cycle repeats, and you should get some good marks anyway. But generally, the questions are quite easy on that, as you'll see later when I show you them. So I've been through what a register is, very small but ultra fast storage that can hold either data or memory. So It is common that they might say, give me 2 registers, but they might say, give me 2 address registers, because they either hold data, which is like a number 7 or 58 or the word H or the letter H, whatever, yeah? Or it holds an address, like a location of something in memory. There are 2 that hold an address, the program counter, because that holds the address of the next instruction, and the MAR, because that holds the address of where we want to get things from main memory. And then there are 2 data registers, the MDR and the accumulator, which I haven't talked about yet. So the MDR holds the data that we got. I'll put that just to stop that bugging out. I don't know why I was moaning about that grammar. It holds the data that we got from main memory. So a minute ago when we did the fetch from RAM, we put where do we want to fetch from RAM, and then that's where the data from RAM appears. And the last one is the accumulator. And think of the accumulator as like a calculator. As you're adding 2 plus 4 plus 6, it will just keep a record of the current result of mathematical calculations, like the current sort of like, you know, because many calculations are multiple steps, aren't they? Like you do 4 steps or 5 steps. And so it's each step that stores the result of any calculations in there. Yeah, so it holds the calculation results. Okay. So the other parts of the CPU you need to know are the ALU, which is the arithmetic, I don't know why I didn't put that, arithmetic logic unit. And that does the maths and the logic checks. And by logic checks, I mean things like 6 greater than 7, and, or, are these 2 things true? Is this true? Is that true? Think of it as like the questions being asked in a program, like is ammo there? You know, have they got ammo? Have they got the key? So that will do the math and do all the logic checks, okay? The control unit is just that controls the flow of data. It controls how the data moves around the CPU. It's also in charge of the clock, which if, I don't know if you can hear me clicking. The clock is like a pulse that goes off like that. And in a second, I'll talk about that. But that basically says go to all the components. So the components all go when the clock ticks. Go, go, go. And the control unit's got that part. I haven't actually seen a question on that yet in any exam. But hey, it is in the course, so we don't know. So von Neumann, what did this genius do? Well, he's a mathematician, really, originally. And what he did was, previously, the CPU did talk to the secondary storage directly. But this was very slow, because then the CPU was sort of constantly having a slow conversation with the secondary storage. So what von Neumann had the idea was, why don't we have a pause at the start, load in the program, and then execute it from main memory. So, for example, here, where I've got Paint up, okay, if I were to look in main memory, paint.exe is in there, and so is this picture. So the data is this picture that I'm drawing, and the instructions are paint.exe. So he had the idea to store the program data, should put program data, and the program instructions in main memory. So paint would be the program instructions, the actual executable program, and the picture or drawing would be the program data. So if I'm so here, for example, this is PowerPoint. So PowerPoint.exe would be the program instructions, but also this PowerPoint is held in main memory. Okay, so that's what von Neumann come up with. A lot of questions on that. They normally ask quite simple ones. So let's look at clock speed, cores, and cache. So clock speed is basically how many FDE cycles can be run per second. It's measured in hertz, so you could get something like a 3.8 gigahertz processor, and that would do 3.8 billion FDE cycles per second. As simple as that. It's just mathematically, that's what it does. Quite a lot, isn't it, when you think about it? So in modern CPUs, they're not a single processor. They're a block of processors, and you can have quad core, 8 core, 12 core. And so if you've got a quad core processor, a bit old now really, you'd have 4 processors in there, okay? And each of those processors is running its own fetch, decode, execute, independent of the others. You can think of it as 4 completely separate brains, okay? It is true that you can make programs that make use of each other and they work together, but they are technically running 4 completely separate things. It just happens to be that those things would end up with a final result that is useful. So what is cache? Right, when you're doing the fetch, decode, execute, you're fetching stuff from main memory, which is fast, but it's still not in the CPU already. And what happens is a lot with programs is they'll get stuck in loops. They'll loop over and over again, like maybe not with 3 instructions, but maybe 100 instructions, and then it'll go back to the first instruction. So basically, you're fetching and decoding the same instructions over and over again, maybe millions of times, right, if it's in a loop forever. And so someone thought, wouldn't it be a clever idea if we get this really fast bit of RAM, really fast bit of storage called cache, much faster than main memory, That is a lot faster. And stick it here inside the CPU, right? And then instead of fetching it from memory, why don't we check if it's in cache? So what happens is when you use data, let's say it holds 16 instructions, which is tiny, obviously. The last 16 instructions that you use would be stored in cache. And then before it gets it from main memory, it will do a quick check to see if it's in cache. And if it is, it will fetch it from there rather than fetching it from the main memory, which obviously is quicker because cache is much faster. A lot of students say, why don't they make main memory out of cache? Well, two reasons. Cache is much more expensive to make. It needs a lot more components. And part of the speed of it is that it is inside the CPU. I know you might think that can't matter, but it really does. The position of how far RAM is from the CPU now, because they run so fast, affects the performance. I remember watching a design on Linux Tech Tips where they had RAM, and the designers realized they had to move RAM like 1 centimeter closer to the CPU on the motherboard, because when it was that far away, it was getting out of sync. So it literally is that distance between the CPU and the RAM matters, and the fact that cache is inside the CPU, as well as the fact that it's made faster with more components, does make a difference. So, in short, cache stores recently used data instructions, speeding up the fetch code execute cycle as often instructions get fetched multiple times, right? So, last but not least, the easiest bit in the whole course, what is an embedded system? Well, it's that. It's a system, it's a small computer with limited function that forms part of a larger system or device or machine. So, a washing machine, microwave, okay? The advantage of using a embedded system over a general purpose CPU or computer like we use, like Intel or AMD, is that the embedded system processors use a lot less power. They're easier to design because they're less complicated. They're far more robust because they're designed for the job they want to do and they don't overcomplicate it. And they're cheaper to make, basically, because obviously what's the point of having a quad-core 8.7 gigahertz computer inside a washing machine? So not rocket science, really. Kids tend to do very well on this question, so I don't need to sort of go on it a lot. Just remember some of the advantages. Use less power, easier to design, more robust, cheaper. And then normally they ask you to name one, There you go. So let's go through I went through the last sort of 5 exams and found the questions that were on these in the real exams, okay? So you can read this out. I'm not going to, I'll read it very quickly. So she doesn't understand what different parts of a computer do, so basically fill in the blanks. So CPU obviously stands for Central Processing Unit. Okay. It's part of the computer that fetches and executes the instructions, not data, because data is just like 7, 4, 2, 1, that are stored in main memory. Although for some reason I'm writing in white letters now. Main memory, okay? The CPU carries some arithmetic something unit. Well, we know that's logic because I explained it a minute ago. And the CU, which is the control unit. Okay, there we go. So not that difficult to answer. Kerry's looking at 2 computers. One has a single core processor and the other has a dual core. Explain why having a dual core processor might improve the performance of the computer. A dual core processor has 2 processors inside it, which can both execute their own. Oh, just realised I'm writing in white. FT cycle at the same time. I will, of course, fix that. At the same time. Look at my good typing there. You probably thought, wow, the server's typing fast, and then realised that he's typing with a crap load of errors. Right, so the dual core processor, 2 processors then. This can speed up the computer as if there are 2 programs running, or a program can make use of multiple cores. Then the workload can be spread onto the other processor. Okay. The key word, I don't know if that's a hyphen, but it looks like it is summed in it. The key thing with this is to mention that you either need to be running, I'll put multiple here, sorry, there we go. Multiple programs running, or a program that can make use of it. A lot of kids forget that you can make a program make use of more cores. Doesn't mean that you have to be running loads of programs, although of course that would be useful. But there you go, that's that question answered. Next one, explain how the cache size can affect the performance. As cache, again I'm being dumb. I'm already going to prep 5.5 now. As cache stores recently used data. What quality typing here? Recently used data or instructions which speed up the fetch part of the FDE cycle, it would be better if more recently used data or instructions were in cache. It's weird I type the same words wrong all the time. By having a larger cache size, in this case 512 kilobytes. Now I'm always a big fan of like doing the math. So that's 8 times the size. So I like to say 8 times because in case they say, you know, we are more likely to have the data we need in cache. There we go. Right. There we go. That's a perfect answer pretty much. As cache stores reaches that instruction yeah, there you go. And the last but not least, easy. No, that's not last but not least because there's 2 more. But the table has 5 statements. Stores data. So RAM and ROM. RAM stores data because ROM stores. Well, both actually could store data, but I'm assuming it's RAM and ROM because they can both store data and instructions because the ROM could have some settings in it. The memory is volatile, so that is RAM. Data will not be lost when the computer is turned off, and that's the opposite of that. So that's ROM. Data is read-only, well, that's read-only memory. It stores current running data and instructions, and that is in that one there. Right, so let's go on to this one. Right, let's have a look. So this one's relatively easy. I just got to name the things. So control unit, send signals to direct the operations, cache, small piece of memory inside that no high-speed memory that stores recently used instructions. I know these aren't the best lines, so prove them. Okay. Keeps the clock in sync. That is also the control unit. As I told you about the clock, click, click, click. Register is a small but fast bit of memory. And the arithmetic logic does all the math. All over the place there with my lines, but there you go. That is the answer to that one. Last but not least, state the purpose of CPU. To execute instructions in the FDE cycle. And I know that you can't see that again, so I'll try and set it black. There we go. Again, I'll spell instructions wrong. State words meant you could put something like, yeah, perform process data and perform calculations. But just put even, I'll be tempted to do input, process, output data as well. But always state FDE cycle, execute instructions. What is member single core processor? A single, I think I could practice by doing core processor is a single component that can execute 2.5 gigahertz, 0.5 billion FDE cycles per second. This is a bit different. There we go. La, 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 la. It's only a single core. This is only a single core processor. I'm just going to put this. I don't think you need to add that. Processor. I put, oh, it says that. 1 processor. I'll put 1 just in case it's confused. Well, I identified 2 registers. Well, MAR, MDR. Could have had millions here. Well, could have millions. I could have program counter. I could have. It says identify, so I haven't got to put. Although I should probably put the long name. Well, that probably would get. You probably would get the marks. I could look in the marks again in a minute, but I think actually you do. But let's get them really because it's good to do it. There we go. Memory data register. Oh, there you go. So that's 1.1 of this. It's not too long a video, so there you go.